So, in the last class what we have done, we have started the simplex algorithm, just the basic concepts we have told. Today let us start with the theory behind the simplex method, that is what kind of theory we are using in simplex method. For this one you consider the LPP, maximize Z equals Cx subject to Ax equals B and the non-negativity condition, that is x greater than 0. Let us make two assumptions. One assumption is this B is greater than equals 0 and the A has the full rank. These two assumptions we are making, that is B greater than equals 0 and A has the rank. Then we can write down A as like this, B and N. Basically this we call as the basis matrix, B is the basis matrix and N is non-basis matrix. That is, from there linearly independent vectors whatever you are getting in terms of the unit matrix, that one will be the basis matrix and this N will be the non-basic matrix. Similarly, your x also can be written as xb and xn, where your xb consists of the xb consists of basic variables and xn consists of non-basic variables. So, x is also I am separating, xb consists of basic variables which corresponds to the basis matrix B and xn consists of non-basis variable corresponds to the non-basis matrix n. There is a theorem. The theorem states that let S equals x such that Ax equals B, x greater than equals 0, where A is m cross n matrix, where A is m cross n matrix and rank of A is equals to m, which is less than n. Then your x is an extreme point. Already we know what is the extreme point. X is an extreme point of the solution set. We can denote it by S if and only if x is a basic feasible solution. So, effectively we are saying by this theorem that if S is a set where such that Ax equals B, x greater than equals 0, where A is your m cross n matrix and rank of A equals m, which is less than n, then x is an extreme point of the solution set S if and only if x is a basic feasible solution. That is, if x is extreme point, then it will be a basic feasible solution. On the other way, if x is basic feasible solution, in that case your x is an extreme point. Let us see this one now. Your Ax is equals to B, which you can write it as, from the earlier one, A can be denoted by this, x can be denoted by xb xn, this is equals B, which implies your B into xb plus n into xn. Simply we can write it B xb plus n into xn is equals to B. So, this is equation number 1. Now, whenever xn is equals to 0, for xn equals 0, which implies that your xb equals B inverse B. From here you can write down. So, say this is equation number 2. Your x b is B inverse B, and since the basic solution you can write it in this form, x b 0 transpose, which is equals to B inverse B 0 transpose. Basic solution is this one, x b 0 transpose is equals to x b is B inverse B. So, B inverse B 0 transpose, and if x is greater than equals 0, which is already mentioned. So, in this case we have already the basic feasible solution. So, for x n equals 0 we have the basic feasible solution if x is greater than equals 0 of the form B inverse B 0 transpose. So, this we are getting. Now, whenever x n is not equals to 0, say if x n is not equals to 0, in that case you are having B x b plus n x b, this is equals B. After manipulation you can write down x b equals B inverse B minus B inverse n into x n. So, this is equation number 3. So, for x n not equals to 0, from equation 1 basically we can write down x b in this form, which is we are denoting as equation number 3. Your z is equals to now C x, and C x means this also we can write it as C b C n and x b x n transpose. In matrix notation we are writing it, so that you will get it as C b x b plus C n x n, and if you put the value of x b from 3 here you will obtain. So, it is basically C b x b plus C n x n. From here you put the value of x b from equation 3, and after manipulation you will obtain C b B inverse B minus C b B inverse n minus C n into x n, which is equation number 4. So, you are getting this. Let us take the other pen. So, you are obtaining z equals this one. Your z is the objective function which you want to optimize. You are getting equation 4. Now, your x b is B inverse B minus B inverse n x n, which I got it in equation 3. In equation 3 you got x b equals B inverse B minus B inverse n x n. So, that only we are writing, and this equals you can write down B inverse B minus summation over j belongs to j B inverse A j into x j. This B inverse n you are writing in this format, B inverse A j into x j, where capital J is the index of non-basic variable. Please note this one. Here J, capital J is the index of non-basic variable. So, using this your z can be written from this equation. If I substitute in this equation 4, z equals this one, I will obtain z equals C b B inverse B minus summation j belongs to capital J C b B inverse A j minus C j into x j. This is our say equation number 5. So, for basic solution obviously we know that your x n should be 0. For basic solution always x n should be 0, so that you can obtain z equals C b B inverse B. So, once you are getting z equals C b B inverse B. Now, from equation 5 I can, if I differentiate z with respect to x j, with respect to the variable x j, del z del x j, this will be equals to minus C b B inverse A j minus C j, and this C inverse C b B inverse A j is nothing but the Z j. This is nothing but Z j. So, this becomes Z j minus C j, where Z j minus C j represents the reduced cost value. Z j minus C j represents the reduced cost value for the jth index. Now, if Z j minus C j, if this is less than 0, this implies del z del x j, which is greater than 0. So, we can say from here that if the non-basic variable value of the non-basic variable x j increases from its current value, then the value of z also will increase. Please note this one, that the value of the non-basic variable x j, if it increases, since the first derivative is greater than 0, therefore, the value of the objective function also will increase. That means, whenever I will manipulate our table, I will check which variable should enter into the basis into the table. For that one, we will calculate the value of z j minus C j, and the most negative z j minus C j we will choose, so that we get the maximum value of the objective function z. So, this we will use whenever we are doing the algorithm, at that time it will be required. So, if you see here, one more thing is there, that is the central idea if of this simplex algorithm is very simple, that is you are starting with an extreme point and you are checking what is the value of the objective function, then you are traversing around the adjacent extreme points one after another, and you are checking what is the value of the objective function at that, and by that way you can obtain the optimum value of the objective function. Since you may be knowing that it is known to us that the value optimum value of the objective function can be obtained only at the extreme point of the feasible region. So, basically what we are doing in simplex algorithm, we are starting with one extreme point, we are checking what is the value of the objective function. If that is not satisfying our criteria, that is z j minus C j is greater than equals 0, in that case we are choosing another extreme point and we are repeating this process. This is the basic idea behind the simplex algorithm. Now, if your BFS will be optimal if z j minus C j is greater than equals 0. From here we can say that if all z j minus C j for all j, if this is greater than equals 0, then the basic feasible solution whatever you have taken, that will be optimum. Whereas, if z j minus C j is greater than 0 for all j, then we say that the optimal solution is unique. Please note this one, optimal solution is unique. So, there are two cases, one is if z j minus C j greater than equals 0, in that case the basic feasible solution will be optimum, and if z j minus C j strictly greater than 0, then the optimum solution is unique. So, in the last class if you remember, we were talking about that we will transform, we have the original problem. The original problem is written in the canonical form. From the canonical form we are writing the corresponding from canonical form we are writing it into the corresponding standard form, and the standard form is written in the form of a table, where some basic variables will be there, some non-basic variables will be there. Now, if your z j minus C j, all z j minus C j are not greater than equals 0, that means the solution is not optimum. So, then I have to find out what should be the entering vector, that means from basis one vector will be going out and one vector will come inside. So, now we will check which vectors will be entering and which vectors will go out. For that one, first let us see this thing, determining the entering variable in basis. Suppose there exists some non-basic variable x j for which the reduced set z j minus c j is less than 0. So, as we have told, if z j minus c j greater than equals 0, we have obtained the optimum solution. So, if there is some variable x j for which z j minus c j less than 0. Now, from this select the index k which belongs to the non-basic variable. Capital J denotes the index of the non-basis variables. From there, I will select k for which z j minus c j is most non-negative. Please note this one, z j minus c j is most non-negative. So, there may be some values, out of that the z j minus c j which gives you the most negative value, that we will choose, and corresponding to that index k, x k will be the entering variable. So, for entering variable, what I have to do? I have to check the value of z j minus c j, and most negative z j minus c j I will choose, and corresponding index and corresponding variable x k will be the entering variable. Now, next one is determination of departing variable, that is which variable will go out from basis. This one, earlier one we told that which basis which variable will be in basis. So, since one vector is going in basis, one vector or one variable should go out. So, next step is for this one. You know your x b is equals to b inverse b minus summation over j belongs to j b inverse a j into x j. Now, suppose x k denotes the entering variable. So, first I am choosing the which one will be the entering variable. So, I am choosing x k as the entering variable. Then I can write down alpha k equals beta b inverse a k, where k belongs to the index of non-basis variable, and from here you can write down a k equals b into alpha k, and alpha k and b into alpha k I can write down summation I equals 1 to m alpha I k into b I. So, your a k can be written by this. So, by replacement theorem of linear algebra, we can say that a k can be replaced by any b such that alpha I k is where alpha I k is not equals 0. So, from here we are saying by replacement theorem of linear algebra, a k can be replaced by any b I provided alpha I k is not equals to 0. I will come to this why alpha I k should not be 0. Now, this implies that del x b del x k, this is equals minus b inverse a k, and which is nothing but minus alpha k. So, that x b becomes b inverse b minus x k alpha k, b inverse b minus x k alpha k. Now, put b inverse b, this is equals beta, and which is nothing but beta 1 beta 2 like this way beta m say. B inverse b I am assuming as beta, and which I am writing as this thing. In that case, you can tell that beta 1 beta 2 like this way beta m minus x k into this, actually this x b always will be greater than equals 0, x k into alpha 1 k, alpha 2 k, like this way alpha m k, and this is greater than equals 0. So, from here x b greater than equals 0, and if I assume b inverse b equals beta, take this column vector, then in terms of column vectors I can write down this thing. Now, from here we can write down x k alpha I k, x k alpha I k is less than equals beta I for all I equals 1, 2, like this way m. So, from there for individual things we can tell that x k alpha I k should be less than equals beta I for all I equals 1 to m, or I can say x k is less than equals minimum of beta I by alpha I k, where such that alpha I k is greater than 0, minimum of this. So, x k now we are saying it should be minimum of any one of this, where I varies from 1 to m. If you assume let L equals I such that beta I by alpha I k is minimum. So, we are assuming L equals I such that beta I by alpha I k is minimum. Then we say that this index L, that means x L will be the departing variable, or in other sense if I have to say, I will say that we are finding the ratio of beta I by alpha I k. Whenever we are solving the problem, we will see to it. So, when beta I by alpha I k is minimum for which value, corresponding to that variable will be the departing variable. So, I think that now it is little bit clear. Whenever I am going for the entering variable, how to use the entering variable, and then how to select the departing variable. So, let us take now one example how to find out the solution of this type of equations. Let us take a problem, maximize z equals 60 x 1 plus 50 x 2, subject to x 1 plus 2 x 2 less than equals 40, 3 x 1 plus 2 x 2 less than equals 60, and x 1 x 2 greater than 0. So, since I have 2 less than equals variables, first thing is I have to convert it into the equality type, the constant, and this equality type I can use by, I can do it by using the slack variable. This we have done earlier, we have told it earlier that whenever you have less than equals type equation, by adding the slack variable I can make it an equality type. So, your problem in standard form I can write it as maximize z equals 60 x 1 plus 50 x 2 subject to x 1 plus 2 x 2 plus x 3, because this is your slack variable and this is equals to 40 we have told. The other one, second one will be 3 x 1 plus 2 x 2, 3 x 1 plus 2 x 2 plus I can write it 0 into x 3 plus x 4 equals to 60. So, here also I can make 0 into x 4, where x 1, x 2, x 3, x 4 all are greater than equals 0. X 1, x 2, x 3, x 4 all are greater than equals 0. So, therefore, what is happening here? Since I have 2 less than equals type of inequality, so I am adding to slack variables x 3 and x 4 and I am adding here. So, what is the cost associated with this? Cost associated with this will be for the variable slack variable always it will be 0. So, in the cost function for the slack variables the coefficient will be always 0. Please note this one, that for slack variable the coefficient in the cost function it will be 0. Now, see this one C b b x b, like this way it is written. If you note here this particular portion, this side if you see, this is forming one linearly independent set of vectors, because unit vector you know it always will be that one. So, what are the variables associated here? X 3 and x 4. Therefore, in your basis basically the variables will be x 3 and x 4. So, this I am writing as x 3 and x 4. So, using this, wherever you are obtaining the unit matrix, corresponding variables will go into basis, those will be basic variables, and the other two variables, that is x 1 and x 2 will be the non basic variables. If you remember, we have told that in the table the first thing is that the first row represents the coefficient of the cost, like for x 1 coefficient in the cost function z is 60. So, we are writing 60, for x 2 it is 50, we are writing 50, for x 3 it is 0, for x 4 it is 0. This b corresponds to these two values 40 and 60. So, I am writing this as 40 and 60, and these coefficients are 1, 2, for x 3 it is 1, it is 0. The next one is 3, coefficient of x 2 is 2, then it is 0 and then it is 1. Your b case we write the variables as a 3 and a 4. For C b, what is C b? C b is the value coefficient of x 3 and x 4 in the cost function. Coefficient of x 3 and x 4 in the cost function, that is this 0 and 0. So, these are the zeros. Now, you have to calculate the value of z j minus C j. Z j minus C j is C b x b minus C j, C b x b minus C j, that is this into this, the 0 into 1 plus 0 into 3 minus 60. So, it will be minus 60 since we have 0 basically. So, it is C b is this part into x b value whatever is there minus C j. So, for the second variable x 2 it will be 0 into 2 plus 0 into 2 minus 50. So, that the value will become minus 50. The next one is 0, next one will also be 0. So, now you see we have told if all z j minus C j greater than equals 0, then only we obtain the optimum value, but for this case that is not true. So, some are non negative, which is the most non negative, here it is minus 60 is the most non negative. So, therefore, this will be the entering vector, this will be the entering vector. So, basically from this basis one variable will go out and x 1 will enter. Next is I have to calculate which variable will depart. For that one I have to calculate the ratio. What is the ratio? Ratio is this b divided by x, nothing else. Whatever that alpha we have told, here it is b divided by x. What is b? Here it is b for this entering variable, this x. So, it will be 40 by 1 and this case it will be 60 by 3. So, therefore, this value 60 by 3 is minimum. So, your outgoing vector will be this thing, outgoing vector is this one. So, in the next table what will happen? X 1 will enter and x 4 will go out. Let us see quickly what happens to the next table. In the next table, in that case what will happen here? In this case for x b it will be x 3 and x 4 will be replaced by this. These values remain same, that is 60, 50, 0 and 0. Your b value is there, sorry, this is x b is x 3 and x 1, this is a 1 and a 3. Corresponding to x 3 and x 1, the cost coefficients corresponding to x 3 it is 0, corresponding to x 1 cost coefficient is 60. So, I am writing 60 over here. Now, what I have to do, if you see this one, you are having this is the departing variable, this is the entering variable. Wherever they meet, that point is known as the pivot element. This point we call it as the pivot element. So, what I have to do in the next table, I will make this pivot element as 1 and in the all other elements of this column, first column, I have to make 0. So, I have to manipulate the matrix in such a way that this element I have to make 1 and all other elements of this table will be 0. So, to make this particular element as 0, I have to divide the entire row by 3. So, that I will obtain here, in this case I will obtain here 20, it was 1, then it is 2 by 3, 0 and 1 by 3, 2 by 3, 0 and 1 by 3, simply by dividing this. Now, how to make this element as 0? This is row 1 minus row 2 by 3 if I make, row 1 minus row 2 by 3. So, in the first case what I have done, I have made it this I obtained by making R 2 divided by 3 to obtain this element as 1, whereas to make this element as 0, row 1 minus row 2 divided by 3. So, I have to start from here itself. So, that it will be 20, row 2 minus this thing, it was 40 and 60. So, this minus 60 by 3, 60 by 3, so it will be 20. So, 40 minus 20, so that you will obtain 20. In the next element, if you see 1 minus 3 by 3, it will be 0. So, we are writing 0. Like this way, we can put the other values 4 by 3, 1 and minus 1 by 3. Now, calculate again Zj minus Cj. In Zj minus Cj, this into this plus this into this minus this. So, 0 into 0 plus 60 into 1 minus 60, it is 0. Next one will be minus 10, you can calculate it, this is 0, this is 20. So, this Zj minus Cj are not greater than equals 0. So, you have one entering vector. So, this will enter, this vector x 2 now will enter into basis. Now, you have to calculate the negative, the which vector will go out. For that one, b divided by this x 2, this I have to use. So, here you will get 20 divided by 4 by 3, and in this case you will obtain 20 divided by 2 by 3. The minimum value you will obtain here. So, therefore, your x 3 will depart. So, in the next table your x 3 will depart. So, that here now x 3 will be replaced by x 2, x 1 will be there, all these values are fixed 0 0. So, corresponding to this it is a 2 and a 1, these values are corresponding to x 2, Cb is 50 corresponding to x 1, this is 60. If you see here, for this the pivot element is 4 by 3 this one. That means, now I have to make this element as 1 and all other elements of this as 0 using the earlier approach whatever we have told. So, I am not explaining that one now, I am directly writing this one. I have to basically divide multiply by 3 by 4 to get it 1. So, in that case other values will be this thing 3 by 4 and minus 1 by 4, and whenever I have to make this x 2 as 0 in this case. So, you will obtain the values as b will be 10, this one is x 1 is 1, then it is 0, then minus half and plus half. Now, if you again calculate this into this 15 to 0, 16 to 1 minus 60 will be 0. This one is 0. This will be 15 by 2 and this is 35 by 2. Now, you see for this case Zj minus Cj greater than equals 0 for all j. Zj minus Cj is greater than equals 0 for all j, and in this case Zj minus Cj is greater than 0 for non-basic variables x3 and x4. So, we obtain the optimum value. What will be the optimum value? The optimum value you can obtain from here, that is x1 will take the b value, that is x1 equals 10, x2 this is equals 15, and the value of z max you can obtain by calculating these values, that is this into this plus this into this. 50 into 15 plus 10 into, I am just writing 50 into 15 plus 10 into 60. So, it will be 1350. So, this is the solution of this problem. So, in the next class we will explain one more example to illustrate this algorithm.